A very good morning to Dr. Shaiful and my fellow friends. Today, we are from Group 8 would like to present the Lab 2 report. Our group stands from 4 members, which is Mohamad Azri bin Zulkhairi, Adri Fahmi bin Azmi Merican, Nirmala Devi A, Balakrishnan, which is me, and Fahim Nazmi bin Khirul Fozi. Now, let me explain on our findings. First and foremost, there are two parts. First is theoretical part, and the second one is regarding the MATLAB coding and the results. So, first question, it's about a square loop wire carrying a clockwise current of 5 ampere is shown in figure 1 as you can see below. Given that the center of the square loop wire is at the origin with the width and length are given by 8 meter respectively and it lies on xy plane, which is z equals to 0, as you know. So, my part is to explain part A, Roman 1. Okay, so let me explain. By using the Biot-Savart's law, derive the equation of the magnetic flux density vector at point P for the line current I. State a final equation in a coordinate system. So first step that we would like to do is assume that the coordinate of LA, LB, LC and LD is such. Okay, then the next step is to rewrite the Biot-Savart's law in this form, which is mu naught I over 4 pi dl times r minus r1 r prime over in modulus r minus r prime cube. So what is r minus r prime? It is actually the vector, resultant vector. Okay, so therefore br is equals to mu naught I over 4 pi integration of L and then dl times r minus r prime over in modulus r minus r prime cube. Okay, therefore you will obtain dh is equals to I dl over 4 pi times the resultant vector over the resultant vector in modulus cube. Therefore, now for the x-axis, let us determine that dl is equals to dx. So to find the resultant vectors, obviously we need to carry out final minus initial. So the final point is, which is point P 0 minus the initial at 0y0. So therefore you obtain negative y plus haz. Therefore, we need to carry out dl times the resultant vector is equals to negative h dx ay minus y dx az. Therefore, the dh, after you substituting all the equation, you will get when you substitute the equation, I'll just explain from here. Negative 1 over 4 pi times dx in bracket hay plus yz y squared plus h2 to the power of 3 over 2. So I written as this. Then now, as what we said just now, assume LA is equals to the given coordinate, right? So now the current is same, which is 5 ampere. Now y equals to negative 2 and z is equals to 0. So you have to integrate the dx, which is equals to negative 4. Okay, then you just substitute the value of dx inside the formula as given. Therefore, finally you will obtain HLA is equals to 5 over pi in bracket HAY minus 2AZ over 4 plus H squared in bracket cube. So the steps is repeated until LD, as you can see here. Then finally, after we obtain until LD, which is HLD, then now we would calculate the total magnetic flux. So it is equals to HLA plus HLB plus HLC plus HLD. So you will have to plus all those 4 equations in order to get this equation, which is 5 over pi square root of the whole thing 4 plus h squared in bracket cube times with negative 8 AZ is equals to negative 40 over pi times with 4 plus h square in bracket 3 over 2 times AZ. So the magnetic flux density B is equals to mu naught times H, where mu naught is a constant. So you will get the equation B is equals to negative 40 over pi in square root plus in square root bracket 4 plus H square in bracket cube times AZ. So that's all from me. Now I would pass to my another group member, Fahim, to explain about part A, Roman 2. Thank you.
Assalamualaikum warahmatullahi wabarakatuh. My name is Fahim Nazmi bin Fozi. My metric number is EA19031, and today I will be continuing with the presentation for part A. The question asks us to plot the magnitude of magnetic field density versus H at point P when H is changed from -5 to 5. In order to answer the question, we will use MATLAB Simulink. To create the graph, we will put the value given to us into the coding. For Fs, which is frequency, is equal to 100. For Ts is time calculation, which is equal to 1 per Fs. T is for set H from -5 to 5. U0 is the permeability of free space, and B is magnetic flux density. From the graph, the X label is Hm, the Y label is the magnitude of magnetic flux density, and the title of the graph is Plot of Magnetic Flux Density Magnitude against H. From the result that we achieve in the graph, we know that when the value of H is 0, we will get the highest magnitude of magnetic flux density. That's all from me. Thank you.
Now, for part B, question A, we are going to simulate the magnetic flux lines produced by the square loop carrying the current as stated in part A, 1 and 2 using a MATLAB. And for the first part here, we show the minimum and maximum, the position of the line, which is the line x is equal to -2, the x equals to 2, y equals to -2, and y equals to 2. And then we set up the number of x division equals to 10, and then number of y division is equal to 10. This is to set up the number of cells in x and y direction. And then here is to compute the step size in both x and y directions, and it will be used for the equation to make the magnetic flux density. Here is the information of the current line, which is the current is 5 ampere. And then this part here is the differential line vector in x direction, negative x direction, y direction, and negative y direction. This is for the direction of the current line for each line. And then for the mu naught here, this is the permeability of the free space, which is 4 pi times 10 to the power of -7. And then here is to set the number of plotting points along x, y, and z axis. And then here is to set the minimum and maximum plotting points on the plane, which is each axis consists of -4 to 4. And then here is to compute the step size in x, y, and z directions. And then from here is to build the arrays of the plot plane. And then this B1 until B4 is to initialize the zero array to fill in the flux density vectors. And starting from here, this is the looping code to make the magnetic flux density vectors. And for the m equals to -1, m equals to 1 until a number of x divisions, this is to make the magnetic flux density at current y equals to 2. Then here is the looping code for the magnetic flux density at current y equals to -2. This is the magnetic flux density at current x equals to 2. And the last one here is the looping code for the magnetic flux density at current x equals to -2. And from there we plot the magnetic flux density and plot the line of the current line in 3D view. And from there, to make the current line even more visible, this is the coding. And from there, here is the result of this coding. Then here, as we can see here, this is the result of the magnetic flux density in using MATLAB. It is the vector line for the magnetic flux density is barely visible, but if we change the view, for example, at here is to change the view, XZ position, XZ view, I mean, we can see the rotation of the magnetic flux density at line x2 equals to 2 and x negative 2. And also, this from the xy view, this is from the top, we can see the direction of the magnetic flux density at each line. And then from the YZ view, and we can see here the rotation of the magnetic flux line in at y, which at current line y equals to 2 and y equals to negative 2. Alright, that is all from me.
So next, I will explain for part B, question B. So basically, the coding are same and similar to from part A, question 2. So I will skip explaining this because my friend already explained it. So I will go straightly on the question, which is the question asks us the characteristic and also how to increase the magnetic flux density. So basically the characteristic from this graph, you can see that it is a bell graph or Gaussian distribution. Basically it is a most common normal distribution. And for the how to increase the magnetic flux density, okay, basically we can say that if the H closer to the current line, the magnetic flux density will be increased, which is we need to take P point close to the current line so that the magnetic flux density will be increasing. How to describe or to state it or to prove why is this happening? We can see on this graph for H equal to -5, the magnetic flux density are only about 0.1 something. But if the H closer to the current line or 0, or basically we can take -1 or 1, the magnetic flux density start to increasing. But if the gap between H and current line are 0, we can see the peak, which is we can get the maximum value of the magnetic flux density. So we need to get to take point P increase closer to the current line to make the magnetic flux density going increasing. So I think that's all from me. Thank you. So I think that's all from us from group 8. Thank you for your time.